Today I'm going to talk about the impact of the equation of state on neutrino opacities in core collapse supernovae. And this is a project that is currently working by, Andrew and I are working together on this project. So as the topic suggested, we are going to talk about the neutrino interactions, which is very important for understanding the core collapse supernovae and the neutron star mergers. And of course, this is a very broad topic, including a lot of complicated problems. And today, what we are focusing on are just the interaction between the neutrinos and the nucleons. So this kind of the interaction will be complicated by the many-body effects if the density is very high. So as what we can see here, the neutrino-nucleon interactions can be mainly classified into two types. The first one is the neutral current interaction, and the second type is the charged current interaction. And it would be very nice if we can just describe both of these two channels in a unified way. And actually that could be done. As what we are looking at here on the above, so actually the differential cross-section for both channels can be written down in a quite similar way as what we can look at here. They are both proportional to this tensor product. So this L tensor is corresponding to the leptonic section. And this this lambda tensor is corresponding to the hadronic section. And additionally, since both the electrons and the neutrinos, they do not have any inner structures anymore. And because of that, this L tensor can be written down in quite a simple way like this. However, for this hadronic tensor, when we are trying to describe the neutrino interactions in a very high density environment, when we are trying to write down this hadronic tensor, we have to consider the inner structures of the many nucleon systems in the very high density environment. And that is where all these many body effects are entering into your calculations and the expressions of the neutrino-nucleon interactions. Of course, I will discuss and introduce all those kind of the many body effects afterwards. But before that, let's just have a very brief overview for all the problems that you might encounter when you are trying to describe the neutrino interactions for core collapse supernovae and the neutron star mergers. So this is a table made by Chuck Horowitz about 20 years ago, but still it is kind of a nice summary. So that's why I'm putting this table here. So for the correction number 1 and the number 2, those are the corrections that already exist for the free space neutrino-nucleon interactions. And I believe that the correction number 1 and the number 2 has already been taken care of by a lot of previous publications and the simulations. And then for the corrections from number 3 down to the number 14, those are the corrections more or less due to the many body effects. And if we are looking at all those corrections more carefully, we will notice that for the correction number 3 to number 5, they are kind of model independent, which means that we can then describe these kind of the corrections explicitly without any worries. However, for corrections from number 6 to number 14, they are not only due to the many body effects, they are also kind of very model dependent, which means that we have to rely on a specific model to describe this kind of the many body effects. And for our work, actually, we have taken care of the correction number 1. We have taken care of the correction number 3, 4, 5, 6, 7. And also, I want to emphasize that in this work, we are focusing on the corrections number 6 and the number 7, which are due to the many body, which are due to the mean field effect and are due to the RPA corrections. So these are the corrections very model dependent, And to be more specific, these kind of the corrections are very sensitive to the model of your equation of state. So let's just move forward. So to begin with, I think it would be better for me to present to you guys a very simple blueprint of attacking such a problem of the neutrino interactions. So first, we start from this very general expression of the neutrino interactions. And then we notice that in a non-relativistic limit, this tensor product can be actually decomposed into two parts. So the first part is corresponding to the vector current channel, and the second part is corresponding to the axial vector current channel. And then you will notice that the many-body effects are now entering into these two channels separately and differently. So for the many-body effects corresponding to the vector current channel, it is now written as a structure factor S of V. And for the, probably I will put it here. And for the axial vector current channel, the many-body effects are now entering into the calculations as the structure factor S of A. And then we might be able to ask how to find out these structure factors. In the linear response theory, they are now proportional to the imaginary part of the polarization functions. So now the problem is becoming how to calculate the polarization functions. And maybe the simplest way is to use the mean field calculations. In such a mean field calculations, the input of these polarization functions would just be some mean field values, such as the potential of the nucleons and the effective mass of the nucleons. And if we want to just go a little beyond this kind of the simple mean field approximations, we might want to consider more excited states, which are now including some particle hole pairs. And in this way, we are using the so-called RPA approximations. So to do that kind of the RPA approximations, we now not only need these mean field values, such as the potentials and the effective mass, we also need these so-called lambda Fermi liquid parameters, which are now describing the residual interactions between the nucleons. But anyway, in this page, I just want to emphasize that all the input for our RPA calculations can actually be derived from a given equation of state. So that's the key point that I want to emphasize. And that is how we are trying to make sure that the underlying equation of state would be then consistent with your neutrino interactions. And finally, in this page, there are another interesting thing is that we will notice that if you want to derive all the input parameters for your RPA calculations from the underlying equation of state, then you have to do them density dependently, because all those parameters are actually in principle density dependent. And if you want to have a fully consistent calculation of the equation of state and the neutrino opacities at the same time, all the calculations has to be done explicitly for a specific density, step by step. So that's the only thing that I want to mention in this page, okay? And then now finally, we can look at how those residual interactions, which is needed for our RPA calculations, looks like at different densities. In the lower density region, our residual interactions are now derived from an explicit zero equation of state. And that kind of new version of the residual interactions is now described as these colorful solid lines in the left panel. And for these dashed colorful lines, those are just taken from a very early but very important publication by Burrows and Sawyer in 1999. So as what we can see here, now the residual interactions for the lower density region, what we are doing is that our residual interaction is now taken from the zero equation of state. So we can see that these solid lines and these dashed lines do have some very obvious deviations. And that is just the meaning that by updating the residual interactions, we might be able to see some difference in our neutrino opacity calculations. Okay, so for the left panel, we are describing the residual interactions in the lower density region. And in the higher density region, we are describing the residual interactions from very low density to very high densities. From very low densities, that is kind of the same for the left as the left panel, which is the zero version of the residual interactions. However, and for the higher density region, we are just trying to describe and derive our residual interactions based on a Skyrm-like models. And we notice that in the higher density region, maybe our knowledge about this equation of state is not enough, and there are a lot of uncertainties over there. So which means that there are a lot of possibilities to trying to describe this kind of the residual interactions based on a lot of different Skyrm models. Although here I am just plotting one version of the Skyrm type of the residual interactions. Actually, in principle, we will have a lot of possibilities over here, and we need to try to understand what's the impact of this uncertainty of the equation of state on this kind of the residual interaction as estimations afterwards. So, okay, I guess this is what I need to say for this page. And finally, we are moving to the result section. So in this section, I am showing you guys the inverse the mean free path. For the upper two panels, I am comparing our new version of the RPA calculations with an exact zero calculations. So the first panel, I am comparing our new RPA calculations with the zero calculations in the axial current channel. And in the left panel, I am comparing our new version of the RPA with the zero in the vector current channel. So for this red solid line, this is the exact zero calculation. And for that black dashed line, this is our new version of the RPA calculations. So this is for the axial, that is for the vector. And then for the third panel, I am showing you guys the total inverse the mean free path. And also I am comparing it with the exact zero calculations. For example, this red solid line is from our zero calculations, and that black dashed line is from our new version of the RPA calculations. And finally, in the last panel, I am showing you guys still the total inverse the mean free path, but at higher neutrino energies, where the incoming neutrino energy now is the 30 MeV, which is kind of a realistic neutrino energies for the Koch-Up supernovae. And also besides the inverse the mean free path in lower density region, I am also plotting the inverse the mean free path for higher density region. And as I have just mentioned, there are a lot of possibilities in the higher density region because we are not quite sure about the equation of state. And right now, I am just plotting one possibilities out of a lot of different possibilities. And this red solid line is the inverse the mean free path of the neutral current interactions based on the N3AS equation of state. So at this point, one might be wondering why bother to use these RPA calculations since we already have these zero calculations. And this zero calculation is describing the neutral current interactions in lower density region with more confidence, with higher confidence and in a more accurate level. So the answer is that comparing to the zero, the RPA is a theory that gives you more predictions. So for example, it not only gives you the neutral current inverse the mean free path in lower density region, it will also be able to give you the whole neutral current neutrino interactions from low to high densities. And also it will also give you a prediction of the charged current neutrino interactions. And the RPA not only gives you the static response of the neutrino interactions, it also gives you the dynamic response of the interactions. So in this way, we can think that at least by using RPA calculations, you can have all the important neutrino interactions in a that all the calculations are self-consistent to each other. So that might be the big advantage of using RPA calculations. And now we already see that in the lower density region and for the neutral current channel, our new version of the RPA is more or less agree with the exact vero calculations. That is a very promising sign for us. And finally, after discussing the neutral current channel, we are moving to the charged current channel. So this left panel is showing you guys the axial vector current of the inverse mean-free path for the charged current channel. And that is based on our new version of the RPA calculations. And for this right panel, it is just showing you the vector part of the inverse mean-free path of the charged current channel. And as I just promised, if you are doing the RPA calculations, you not only have the static response, you also have the dynamic response, as what we can see here. So here I am showing you guys the axial part of the dynamic response of the neutral current interactions. And also in this page, we can also see the impact from the equation of states on the neutrino opacities. Because for example, if we are focusing on the last panel, this is the dynamic response at around saturation densities. And then you can see that this dynamic response has a lot of possibilities. And all these different possibilities are just due to the effect that we are using some slightly different nuclear input. And that slightly different nuclear input are just because that we are not quite sure about the equation of states there. And that's why you will see that the dynamic response has uncertainties. So to conclude, the situation is that the uncertainties of your equation of state is now propagating into the calculation of your neutrino opacities, because we are now calculating both things self-consistently. And as what we can see here, I am also giving you guys the relative uncertainty of the total axial cross-sections at different densities. So when the density is increasing, this kind of the relative uncertainties is also increasing as what we expected. So this is for the neutral current, and that is for the charged current. So actually, the behavior of the charged current is more or less similar to the neutral current, that the uncertainties of your neutrino opacities will becoming bigger and bigger when the density is gradually increasing. So that's what we expected and what we can see from here. Okay, so finally, we have already seen that how we can produce the equation of state and the neutrino opacity at the same time and in a consistent way. And we also see that the uncertainties of your equation of state are now propagating to your understanding of the neutrino opacities. And probably the next step would be try to understand the uncertainties of your equation of state and the uncertainties of your neutrino opacities, how they are relating to each other. So to understand the relationship between these two types of uncertainties, probably we should rely on this kind of the correlation matrix. So for example, the first correlation matrix that I am showing you guys is the correlation between the model parameters and the model parameters. And that's why you guys will see that all the diagonal blocks are red, indicating a very high resolutions. That is just simply because all these blocks are representing the resolution between the parameter and itself. However, for some off-diagonal blocks, you can still see some very red color indicating some higher correlations. And that correlations between the model parameters, in my understanding, it is emphasizing the importance that when we are doing the calibration of all these parameters, we need to take care of all of them with high correlations. And we need to determine all the parameters with high correlations at the same accuracy level. If we don't do that, then maybe the theoretical predictions will be far away from the experimental observations. And finally, the second correlation map is about the correlation between the observables and the observables. So in our case, our observable would be the inverse the mean free path in different channels. For example, the charged current channel, the neutral current channel, or the vector current channel, and the axial vector current channel. And in this way, you would see that besides the diagonal blocks, which are all red, there are still some off-diagonal blocks that have a relatively high correlations. And the strong correlation between these observables so actually provides a very clear way of the determination of some observables that is not experimentally accessible. For example, let's just assume that observable A is experimentally accessible, but observable B is not. However, observable A, these A and B, they have high correlations. Then probably we can just determine A. And in this way, since B and A are highly correlating to each other, then probably in this way, we will be able to gain some information about the observer B, which is not really experimentally observable. And here, the last correlation map, I am showing you guys the correlations between the observables and the model parameters. This kind of map can be understood more naively because the strong correlations between them are just revealing the sensitivity of the parameters to a particular kind of the physics or the observables. So, and I guess this would be the final page of my result. And now we are moving to the conclusion part. So the conclusion is that first, the random phase approximation is providing us a very systematic way to estimate the neutrino opacities for both the charged current and the neutral current interactions from low to high densities. And also it gives you both the static and the dynamic response. And the second thing is that now our equation of state and the RPA neutrino opacities are generated together in a consistent way. And in this way, the uncertainties of your equation of state will now be able to propagate into the calculation of the neutrino opacities, especially at higher densities. As for the lower density region, we have observed that our new version of the RPA are now having a better agreement with the exact visual response in the neutral current channel. And that is a very promising sign for us too. And for this new version of the RPA calculations. And looking forward, in this point, at this moment, I just want to emphasize that the role of the collective mode in the neutrino opacity might need to be revisited with our updated nuclear residue interactions. Because as we know, the appearance of the collective mode is very sensitive to the value of your nuclear residue interactions. And now, since we are deriving all the residue interactions consistent with our equation of state, and they are changing as a function of the density, so probably in certain region of the density, we might observe the appearance of the collective mode, and that will somehow amplifying your neutrino opacities, making it bigger. But still, this is kind of an open question, and we are still investigating it. And finally, I just want to emphasize that probably we need to switch our non-relativistic calculations into a relativistic one if we want to describe the neutrino interactions more accurately at around the saturation density or at the density above the saturation. Yeah. And I guess that will be a very nice end for my talk. Thanks everyone for your attention.
Thank you, Zidu, for this very nice 25-minute talk. I see there is a question George put in the chat window. Do you mind asking it yourself?
Sure. So thank you. Very, very nice talk. So I had a question kind of upstream. So the question, well, actually, it's kind of related to the last bullet on your slide, on your conclusion slide as well. So the first thing I wanted to ask is about liquid structure factors in the medium. So for example, if I don't have uniform matter and I have lumps, that can be a significant issue in the opacity, right? If the lump is smaller than, say, the wavelength of the neutrinos, which is likely to be the case. So I know in early neutrino transport studies, this was a point of contention. So can you comment on that?
Yeah, sure. So yeah, let me just make sure that I understand your question, George. So you are asking that what would be the effects if the medium is non-uniform? Is that your question?
That is correct. If it's lumpy, for example. So you could even imagine sort of a lattice of, and of course, it's likely to be mostly of interest at densities below saturation density.
Yeah, of course. For example, like the nucleopasta.
Or a bit higher than that. I mean, just if you have a medium and it's kind of lumpy for whatever reason, minimizing some Coulomb energy or something like that, the sizes of those fluctuations might be in a regime that's interesting for influencing the opacity.
Okay, so probably I cannot have a very good comment on these things. So my understanding of this ununiform, of that kind of the non-uniform nuclear medium is coming from the calculation of the neutrino nucleopasta calculations. And in that kind of the study, we will see that if your nuclear medium is non-uniform, then probably, I mean, if you have some kind of the periodic structure of your nuclear medium, then probably that will induce some collective scattering peaks over there. And that will also somehow strongly somehow alternate your original neutrino opacity calculations. So yeah, this kind of the non-uniform medium, I think it is really dependent on the structure of this non-uniform medium, and the detailed structure of those things might have a very big effect on the exact neutrino opacity calculations. And I believe that that kind of the non-uniform effect can be also described by using some structure factors. Yeah, that's what I'm thinking.
I was getting at, and it's related to bullet A on your conclusion slide also. I mean, bullet A there is the response of the medium, right, to the neutrino probe. But if there are structures there already, that might have a different response.
Yeah, I agree. Yeah, and but still, I mean, up to now in this project we are just focusing on the neutrino nucleon scatterings, and we haven't even included the nucleus into it. Yeah. So there is still a long way to go, I have to say.
Very good. Yeah. Very good. Thank you very much. This is very nice.
Thanks so much for the question, George.
The next question is from Joe Carson. He's asking, what different EoS did you use around saturation density? How different are they?
At saturation density? I'm sorry, Sophia, can you repeat the question?
EoS around saturation density. What kind of EoS have you used? How different they are?
Yeah, right. So I think that might be a better question for Andrew, because Andrew is preparing all the different equational states for me.
Yes, Andrew, please, if you
so I did the equation of state side. We did it with my previous graduate student. Around saturation density, we're in beta equilibrium right now for this particular calculation. So the electron fraction is relatively low. We're close to neutron matter. And our equation of state of neutron matter is just based on on calculations from Ingotevs. It's just the uncertainty in the symmetry energy and its derivative, for example, as you would get from that sort of the many body perturbation theory calculations.
Yeah, I mean, so to conclude that, as what we can see here, because of the uncertainties of the equation of state at saturation densities, the total cross-sections of the neutrino opacities are now having, I mean, the relative uncertainty of the corresponding neutrino interactions are having uncertainty at the order of something like 30% or 40%. That is relative, that is very big. So actually, my question is that if the neutrino opacity at around saturation density is that high, will that bring some difference or bring some effect on the core collapse supernovae simulations or neutron star simulations? That might be a question for the people doing simulations. So, but maybe we can discuss afterwards.
Great. So Sanjay, you are the next.
As you do. I apologize, I got to your talk a little bit late. So I have more of a clarification question. Are you, when you say you're doing RPA, are you doing RPA at the one particle, one hole plus collective modes, or are you including two particle, two hole states, which give rise to smearing of the response and you know, they care about the lifetime of the nucleons in the medium?
I guess I'm using the simplest version of the RPA. I am not considering multi-hole and multi-particles. Yeah, and I mean, right now our calculations do not have any dependencies on the lifetimes of those excited states. I guess, yeah.
Okay. And another question is, have you tried to calculate, you know, given your liquid structure function, have you tried to calculate the sum rules associated with those structure functions and compared them to the predictions of the equation of state? Because the sum rules can be related to the equation of state.
Yes, I agree. So we didn't really explicitly calculate the sum rules, but we have compiled the neutral current derivative, our neutral current result with the zero one. And I think the zero one will be able to agree, I mean, to satisfy the sum rules, I mean, 100%. So yeah, but I mean, the sum rules, I mean, for the, yeah, we need to, I mean, we haven't done that, but probably we should do that, yeah.
Okay, thank you. I like I only got the second part of your talk, and it's very interesting to make these correlation, understand how the different observables are correlated. Thanks.
Thank you, Sanjay. Yeah, thanks.
Please, if you have more questions for Zidu, please feel free to unmute yourself or raise your hand. I do not see more questions. Okay, so let's conclude our official part of the seminar and see you next week. We'll have some informal discussion if you would like to stay.
Thank you, everyone.